Thanks, Hal. So, this title of this talk is a little bit tongue-in-cheek. We only have 20 minutes. We know it's lunch afterwards, so we're not going to try and teach you everything, but show you a couple of cool things. Hope you get inspired. And one of the reasons that we were inspired to make this presentation was because data science is very popular now, and we're seeing an influx of people that have perhaps more of a math background and other kinds of sciences, perhaps even social sciences, and have had that as their main focus instead of computer science. So we want to show a little bit what being computer savvy can do for you. How Velix and I work at a company called Laketide. We're based here in Kista in Stockholm. We're a niche data science consultancy. We do machine learning, robotics, IoT, big data, and every other hype word you'll find out there today. The only difference is we're super excited about it, so we're not out to sell anything. But if you have a cool project, we'll kill it. So that's us playing. We've been involved in these conferences for a couple of years. We like keyboards a lot. We're working very closely with NVIDIA on a number of projects, and that's how rocking and programming on many computers at once, because that's how we rock.
High performance.
High performance in every respect. All right, so what we're going to talk about today is binary is better for everything. We're going to give you 3 demos. And we're going to use one data set. It's a small data set we created just for fun. It's 250 million GPS positions. And you might imagine that these positions come into your system from devices, maybe trackers on some cars or something like that. And they're coming from the internet. They have to be aggregated somehow. You want to analyze them somehow. You want to do some AI on them somehow. And then something's going to happen on the other side. And so, there are a lot of popular data formats like Json and JavaScript and HTML and all that soft stuff. But there's a lot to gain from going binary and knowing a little bit about how the computers actually have to work with this data. So we're going to start off with the first demo, which is how to handle the data when it's sent over the network. And Hao is going to demo that.
Thank you. So let's first look at our tiny data. It's about 5 gigs in CSV format. And for each message, it's just, let and long. And basically, it's 2 numbers. And so our end goal is to save them into a file very efficiently and have the fastest way to plot them out or do other stuff. So let's see. How do we gonna send them to our data center or to our computer in the first place? So the first thing up to my mind is, I can just use JSON. The good thing about JSON is it has the data structure. As you can see, you have the let, long, and you know which number is which. But to computer, it's many bytes because it's a string, and you have a lot of redundant data structure, send it over again and again. So it's not very efficient, and you're generating a lot of garbage in the network. So how about let's just remove the let and long? But still, you're still left with a string. So string, each character is 2 bytes, so it's still a lot. So let's just do the native way. Let's just do the let long, 2 numbers. So let's see. We have 2 float 32. 32 bits, it's basically just 4 bytes. So it's going to be super efficient, and this is our most compact way to send this tiny information throughout the network. And you guys might think, you guys just cheating. You have very simple data sets. I have a super complex data structure. I need to let my the receiver side to know what I'm sending. There are very classic ways doing that. And for example, it's called one of the classics is ASM1, and it's called the Abstract Syntax Notation 1. So they use this technology back to 70s, send people onto the moon. So imagine back then, you have to use JSON, send your commands to the Armstrong, and then he do stuff. That's not super efficient. So you have to both pack your data and your data structure in most efficient way. And as here you can see, it's very few bytes sending all the data structure. So let's move on to some demos. Okay, Robert, if now you can start the JSON sending part. So on the bottom you can see our 4 files, and as you can see they are .julia.jl. So we're using this language called Julia. It's high performance, and it also allows us to do very low-level stuff, very high performance also. So we love it. And here is our JSON sender. As you can see in this simple demo, I randomly generate 5 million messages, and I compact them into a JSON string and send through the network. And Robert, if you can jump to receive JSON. So on the receiver side, we have to parse our big-ass string out from the binary first. Then we parse it into our data structure and get the lat long and write to a CSV. So as you can see on the top, the sending is finished. It took 17 seconds. Maybe it's not bad, but let's try the binary version. So now let's move to run the code. And we can jump to the sending bin file. Oh, yeah, it's pretty much done. Okay. Anyway, so in this file, everything is pretty much same. The only difference is after we randomly generate the 2 numbers, we just send it off because it's already the very native language. And on the receiver side, if you can jump to the, yeah. So on the receiver side, when we receive the data, we can just pipe them into our binary file. That's it. We don't have to do anything. We don't want to save it to a CSV. And as you can see, it's only took 4 seconds.
So how much bigger is the CSV file than the binary file?
Yeah, so the CSV is about 5 gigabytes. And our binary one is 2 gigabytes.
I take it if you were to gzip the CSV, it would probably get a little bit smaller, maybe
even
match
exactly.
the binary file.
It's actually very easy to use Julia to do gzip at the hardware level. Just when
but I think the interesting part here is that it's not the size of the data that causes the big difference in speed.
Yeah, exactly. It's redundant data type conversion. So you come back to the native and come back to the data. So it's a lot of redundancy there. So what we're doing is just reducing them. And it's good to think about that. So now we have our data set. And I will hand it to Robert. And he can do his magic show.
Yeah. Well, I think the cool thing here is you might be tempted to think, well, Julia, great, it's fast. Or, now sending the data is fast. I don't have a bandwidth problem. Well, maybe you don't have one now. Another issue is if you want to do things in real time, you sort of have a hard limit on how much time you're allowed to do things. So if you can't meet the performance requirements, then you can't do the real-time processing, and then you're screwed. So I want to show a little bit the advantage of keeping it in a binary format to begin with, rather than converting it from JSON to CSV to float, back to JSON, and doing all these weird type conversions. Let's take a look at these files quickly again. We have, here we go. We have data bin, it's 2 gigs. And we have data CSV, it's 5 gigs. So those are the 2 files. I have 2 Julia programs, a drawing program and a benchmark program. The drawing program is for drawing GPS coordinates on a canvas. So it just does some what do you call it, geodesic stuff and converting those coordinates. But let's start by showing off here. I have a canvas. It's just white, and we want to draw stuff. And how many people here use PyPlot and have tried to plot 100,000 points or more in PyPlot? It's not always super convenient. What about plotting 1 million points, or 100 million points, or 1 billion points? Yeah, with GIS. Well, so you start whipping out the big data tools, but you don't need to because you can do it in the terminal with poor little laptop here. So let's go ahead and start this off. The first thing we want to show is a little bit what it's like to load the CSV file so that you can start working with it. Oh, what happened? It froze. No, it went. Okay, so it took about 4 seconds, except I'm only kidding. This was the small CSV file that was 20 megs. It's not the 5 gig CSV file, and I'm not going to show you how long it takes to load the 5 gig CSV file. The other thing worth noticing is that this 20 meg CSV file took 200 megs of memory allocations in the runtime to parse and load into memory. I didn't load the values into memory, or the CSV, the text string values. I only loaded the float values that it parsed into memory. Since you see here I said use mmap. So I never loaded the CSV into memory. All I had to do was read it, convert it to float, do a number of other things, and then I could start working with the data. That's super inconvenient. You don't have to do that. How has already sent me all the data in float format, so I don't need to change anything. I'm going to go ahead here, and I've included the drawing code. I can just go ahead and show it to you for fun. It has dimensions divided by scale and offset and lat long, and that's basically it. And so we're going to see here, if we try to take that file, memory map it so that we don't have to lift it into memory. We just read straight from the disk. And then we map that onto the canvas. And then we render it. And we draw it onto the screen. How many people think will take 4 seconds? No one thinks it'll take more seconds. I'll take that as a challenge. We'll go ahead and run it here. It's already done. It took 0.6 seconds to load the 250 million points off the disk, process them, and then draw them onto screen. On my laptop, it's a 4-core laptop. So if you guys are struggling with your billion-row data sets, trying to wrangle them with the awesome big data tool across a cluster of computers, just remember that you can do billion-point stuff in less than a second on a laptop if you stick to binary and do some hacky stuff. So the point here is a little bit, we have the data coming in a good format. We have the data being processed in a good format. The last step would be to change your algorithms to be also in a good format. And we want to apply machine learning. So we have a resident expert here that's been working on binary neural networks. And he's going to explain exactly what that is.
Right. Thank you, Robert. Thank you, Hal. So I would like to talk to you about network binarization, the neural network binarization. We have seen that binary data formats can do a lot of different things. And in the context of neural networks, they're mainly used for compression. We know that neural networks suffer from overparameterization. All those full precision values are not exactly necessary. And there are a lot of ways to deal with that. One of those is what you can see on screen right there. It's just to do away with the number itself and only keep the sign of it. So for its positive number, we just keep 1, and for its negative number, we just keep -1. This operation is incredibly easy to do. It's basically just a comparison with 0. So let's run that, and then apply the sign function we just defined on a random 3x3 vector. You can see that what it returns is just a vector, a matrix of -1 and 1s. Now, this is a very valuable representation because we have already compressed our full precision values down to just -1s and 1s, and we can actually map them directly to the binary 1 and 0, right? So we just keep the 1s as 1s, and we just map -1s to 0. And then we can directly map them to true and false. You can already see that this kind of representation is much cheaper, right? We can directly save binary data, which takes much less space than full precision values. But now that we have reached this point, we can define those two functions to do exactly that, to turn -1s and 1s to binary data. And if we apply that function to the previous 3x3 random matrix, we can see that it returns the binary values.
What's the difference between the bit array that you're showing now and an array of Booleans?
Well, this data structure is specific to Julia, and it's one of the reasons that we really like this language, right? This bit array basically does bit packing for us. So we don't really need to do any of those stuff. This bit array uses a true 1 bit to store 1 bit.
So just 1 bit instead of
Yep.
a uint 8 that's set to 1 or 0.
Exactly,
So
exactly.
it's at least 8 times smaller.
At least, yeah. And that comes baked into Julia. We didn't have to do anything to get that functionality. But now that we have it, we can actually start doing some even cooler stuff. We can actually start redefining mathematics themselves, or at least part of it. And the parts that we're interested in redefining is multiplication and summation. Now, element-wise multiplication between two vectors of -1s and 1s is pretty straightforward. You just multiply -1 by 1 and you get -1, right? The exact same operation, or the equivalent operation when you have binary data, is the Exner operation. As you can see here, keeping in mind that zeros are -1s, if we Exner a 0 with an 1, we get a 0, so it's a -1. And then the corresponding true and false values. That way, we are actually able to redefine vector multiplication. So let's go ahead and define the Exner function. And we can see that if we apply the binary multiplication, we get the exact same result as we get when we apply the, the full precision multiplication. This up here is the full precision multiplication, and this is the binary multiplication.
I think it's a little cool to point out that you implemented Exnor in a way that I didn't think to implement it, which was just using a regular old equals sign.
Right.
But when you look at the assembler output, it does use Exnor internally, which is very cool.
Yeah, if you check the Wikipedia page for the Exner operation, it's the formula itself is much more complicated, but at the end of the day, it's just that, an element-wise equality operation.
Yeah.
And now that we have defined multiplication, let's define summation, right? If we sum over, we can sum over a vector of binary values by using an operation called pop count. And pop count is a built-in operation, so it's very cheap, but the problem is that it just returns the count of ones in our vector. We also want to subtract the number of zeros. As you can see here, if we sum over this vector, we want to get back -1, right? So it's -1, +1, -1, we get -1. And to achieve that, we can, as I said, use the pop count operation, which is hidden behind the Julia count function, like that. And we can see that the sum over a vector that has been that is a result of a regular multiplication, and the sum over a vector that's a result of the Exner operation is exactly the same. Having defined the multiplication between two vectors and the summation over a vector, we can actually redefine the whole matrix multiplication operation, which is what I do here. I won't go into detail, but it's pretty straightforward code. We just go over the matrix column by column and multiply it by the vector. And having defined the matrix multiplication, we can actually now start using binary weights and binary activations in neural networks, right? So if we define a typical matrix, a weight matrix in a neural network and put, we can turn everything into binary, having used the previously defined functions. See that the result we get is what we would expect, right? If you multiply the input by a weight matrix, you get a vector of 4,096 elements in this case, which is exactly what we wanted when we defined the layer, let's say. But, oh, right. And we can see that, again, the result is exactly the same. If we compare the result of the full precision multiplication with the binary one, the result is exactly the same. But the thing is, I have gone over all of those things, which seem a bit complicated. But what's the gain? The gain is an execution time. It's much, much faster, as you will see. So the regular multiplication took 2.4 milliseconds, which is, it's not a long time, right? It's very little time. It will be hard to beat.
And is this including like simmed acceleration and other things?
Yep. It includes all of those things. So, you know, it's already optimized, so it's going to be hard to beat.
It's very fast.
Right? Let's see.
I don't think it's going to beat it. I mean,
See?
Wow.
We were able actually to beat it by about 4 times using binary multiplication. I hope this advantage is clear. And as we can see here, the difference in execution times only grows as the matrices themselves grow. So binarize your models as well.
why isn't it always 8 times faster if it's 8 times smaller? If why isn't it just like a linear correlation?
Well, at the basic level, it has to do with the way the multiplication is defined, right? It takes up many more gates, essentially, than just doing a binary matrix multiplication. So that's why the regular full precision multiplication grows faster than the binary one.
I guess the full precision one is doing many more, is not actually doing the same thing even.
Yeah, no, absolutely not. It's there are different things at a very basic level when we're working with binary data.
So the gap
and
just
full precision
increases
data.
if
Yeah.
the matrices increase in size.
Yep.
Cool. Well, those were 3 little examples on how you can gain enormous speed-ups in your data, maintain precision, maintain high throughput, and everything. These types of hacks are ready at your fingertips if you whip out a little hex editor and some other computer science skills. I implore you to go ahead and do that and hope that inspired you. So I think lunch is going to be waiting outside, but if anybody has any questions, we
Question
can take them
time.
now real quick.